Alright, so today is day 70. I did 5 more lead code problems. We are at 44 out of 150, although I think I'm gonna do just focus on 75 because I realized there is some sort of diminishing returns of doing more lead code problems. I think it's better to focus on other stuff, also because you forget the solutions and things like this. So yeah, so let's go ahead and solve the 5 problems that I did again. So the first problem, it's this one, which is very hard. It's the merge k sorted linked list. So we're given k sorted linked list and we have to merge them. So in order to do this, most of the problems, the solutions stem out of making essential observations. So in this one in particular, we have like some sort of list, right? Which is gonna be, we're gonna have k list. This is one, we're gonna have, I don't know, another, and we're gonna have another k list, right? And what we want to do is to make a linked list, right? That is gonna have first this element, then this and this and so on, right? In order. So what we see, the first observation that we make is making this merge linked list is the same as taking one element at each iteration from one of the array, right? So the second observation we're gonna make to solve this problem is what would be the property, like the nature of this decision. And the nature of the decision is that we're gonna take a value that is the minimum among the 3 lists, and we know that the lists are ordered. So essentially now the question translates to which structure it's the best of like keeping track in an easy way and in an efficient way the minimum element for some given amount of numbers. And the answer is we can use a min heap. That's it. And because a min heap, we are dealing with linked list, so a linked list points to the head, so it's gonna be pointing like to the first element. All of these, we have to understand them. They are not values, but they are nodes. So a heap is gonna have, like, if we make a min heap out of the heads of this, it's gonna look like this: 1, 2, and 4, right? So we can do pop. We know that the heap is gonna store the minimum value of the root, and when we push a value, the heap is gonna reorder itself such that the minimum value is gonna always stay at the root. So that's it. That's like the whole solution. Because what we can do is push the heads to a heap, then every time at every iteration, while the heap is not empty, we have to pop this value and move to the next, push this one to the heap, and then we pop it, push it to the heap, then we pop this one, push this one to the heap, then with this one, and I mean now it's none, so we don't need to push anything to the heap, and so on. So this is the intuition, that's the solution, and we just have to take into account the references, because we are not building like the list of values, but instead we have to return a linked list. So we first have to build the heap, so it's going to be like an empty list, and for node int lists we are gonna push to the heap. So I'm gonna use import heap queue. I'm gonna use like the default library of Python, and we know that we don't want to push if it's none, so I'm just gonna say if node. So if node is not none, then I'm gonna push it to the heap. So I'm gonna say heap queue, and I'm gonna call the method heap push. This is the name of the method, and we're gonna push the node. But the thing is, like, the node is a class, it's an object. So in order for Python to know how to do like the reordering of the heap, it needs to have like a condition to compare the values. And unless we can modify like this class and overcharge like the minus or the greater or less than, it cannot perform the comparison. So we know that the comparison has to be performed over the value. So yeah, we have to push this value to the heap, and we have to indicate, okay, push it to the heap and do the comparison with this value. But the thing is that we need to return the linked list. So when we do a pop from the heap, we want to point the pointer of the attribute next of the node to next value, but this is not going to be possible if we retrieve just the value. So we need to give it also the actual node itself. And by default, heap queue is gonna take, the decision it's gonna take of how to arrange it based on the minimum value is gonna be based on the first element, so it's alright. But then we have another issue, which is what happens if node val, if the value repeats, so it's gonna check the second value. And the thing is, like, the second value cannot be compared because it's an object, it's not a value. So we can say, like, if this one repeats itself, then I gotta compare it with something unique, so I can use ID. I mean, we can also use an iterator or something else, but I think this is the simplest. Now we can go ahead and do the while loop. So it's gonna be like while heap. We are gonna first change the references, so I gotta use this trick, which is the one of first defining dummy, and we're gonna define it as we have some isolated node which value 0, and this at the beginning is also gonna be the tail. Then we are gonna pop from the minimum value, we're gonna pop it from the heap. So I'm gonna burn like these characters because we know that the heap, every element in the heap is a triplet, and the first two values of the triplet we don't care, we just care about the node. This is gonna be heap queue heap pop, and we need to pass, we are doing this. And now we need to change the references, because now dummy points towards nothing. Tail is dummy, and at the first iteration we want it to point like to the actual node, so it's gonna be tail equal node, tail.next, because it's the reference, and then we have to update the tail, which is gonna be tail.next, right? And now we need to essentially, we have 1, 2, 3, and we have another 4, 6. What I did was, to the linked list, I started at 0. Then the heap had this value, the 1 and the 4. I said, do pop. So now 1 is here, and then I say tail.next equal node. So I'm changing the pointer of this node towards the next one, and I'm moving tail instead of being 0, because it was 0 at the beginning. Now it's 1. And I need to push this value into the heap now. So that's the only thing we need to do next, but only if it's not like in the last element, because otherwise it's gonna be none. And this value is gonna correspond to the next of this one. So I can say if node.next, so if it's not none, then we're gonna push it, and to push it, essentially we do the same, but of .next. We do it for the next value, and at the last iteration we would pop everything except tail is going to be pointing towards here, and we need to set that 6 points to none. So I have to say tail.next in the last iteration is going to be none, because heap is going to be empty, so we need to update manually the last iteration, and we gotta return the head of the first element, which is gonna be this one. So we know that dummy is 0, so we have to return what dummy points to, so it's gonna be .next. Okay, there is okay, good. The indentation was not okay, but okay, we solved the problem. Let's go to the next 4 ones. Alright, let's start with this one, invert 3. So essentially we're given a tree, and we have to change the left and the right children for every node in the tree. So for one, we change the left is 2 and the right is 3. We need to change it to 3 and 2. And then once the 3 is changed, we need to change the children is 7 and 6. We need to change to 6 and 7. 6 and 7 change to 7 and 6, yes. Alright, so now what observations are like key in these types of problems? First, I realized that for recursion, it's quite easy to debug from the end. To implement the logic is like from the beginning, right? And the debugging is like from the end. And the most important thing, you are going to have like the stopping condition, and that's when you think about the implementation, because in this case we don't, I mean, at the end, the first time we call the function, we need to return a value, so we can directly return something, which is actually the root, right? So we don't care about the return functions of the children, but we know that we're going to call it on the children, right? So what would be like, what are we essentially doing? For a given root, and the root is a node, it's going to have like two children, and we need simply to swap the references. So I have to say root.left and root.right. These change values, so nice this. And we need to do this. So if we call invert 3 in the first node, we're going to swap the children, and then we need to pass this function that is going to swap also in the children of the children, right? And they're going to call it, and so on and so on. So it's simply just calling this again, but I have to call it self.invert3, and I have to put it root.left, and we call it to the first child and then to the second one, and we gotta take care of the edge case, which is gonna be in the last node. The children is gonna be none, and none is not gonna have attribute left. So I just have to return something if it's none. So if not root, so if it's none, I'm gonna return none and submit. Alright, so now we did this one. Let's do another one. Maximum depth of binary tree. Let's go. So in this one, the main observation, we gotta return the maximum depth of a binary tree, and the main observation is that normally in recursion we run the function for each node, right? So the first observation that we do is that the height of the root is dependent of the height of the children, right? And now you ask yourself, what is the relationship? And then you can debug from the end. So you say, okay, the height of the last node is just 1, and the height of the 3 is 1 plus 1 is 2. Then the height of 1 is 1 more, which is 3, right? So it's 1 plus the maximum value between the children. That's it. So when we run the function, we can directly say return 1 plus the maximum value of running the function. Yeah, self.maxDef when you run it for the left child. So it's gonna be root.left. And for the right child. I mean, that's it. And you just have to take into account the stopping condition, like the edge case, which is if you ask yourself this one, and then a root of left is going to be none. So when it's none, the height is going to be 0. So you say if not root, then return 0. And I mean, it makes sense because the max between 0 and 0, it's going to be 1. So it's okay. We submit. Okay, let's go. Let's do the next one. Now we check symmetry. Let's do it. Okay, I have the solution. I forgot to reset. Alright, for symmetry, what we do is we check if the value is the same, and then we call let me think about it. I don't remember the solution that much. So what observations can we say in order to get the solution? For a given node, we check if the value is the same. I mean, we can start with that. So I can say if p.val is different than q.val, it means that we have to return false. So it is not the same binary tree. Okay. If not, I mean, if this is the same, like if it's not different, we are not gonna stop it. So we need to run it on the children. And when I run it from the children, I'm gonna save also this, check this condition. So it's gonna be okay. I just have to also run it. And in order for this binary tree to be true, it needs to be true this value for both nodes of the children. So I have to say self dot is same tree for p dot left and q dot left, and the other child, which is right. And now we have to take care of the edge cases, which is gonna be what happens when I try to check the left child of the last node, which is gonna be none, and the left child of the right node, which is gonna be none. So now we have to ask ourselves, if both of them, I mean, I can give like a quick, I mean, I have A, B, C, D, and I have A, B, C. Like this is not the same subtree because this one is connected to something else that this one is not connected, right? So I can say directly if both of them, like the left and the child, points to none, then we have to return true. So if not P and not Q, we're gonna return true. But if one of them is not, like in this case, because here B, the right child, points to none, but the left one points to something else, then we have to return false. So I can say if either of them, so basically I'm saying if not P or not Q, return false, but I can put, because it's the same condition, so I can put it here. And that's it. We submit. And for the last one, for this function, for this last lead code, we have to check if a subtree is, if this subtree is a subtree of this tree. And to do this, we already have a function that check if this is the same tree. So what we can do is to run for every node in the original tree, check if at that level this is a subtree or not. So we're gonna reuse this function. I'm gonna call it same. I'm gonna call it is same tree, and we pass P and Q, and we delete the self. I can let it. I think it's cleaner probably if I left it. I just need to do this. So we have a way to check if one tree is the same as the other tree. Now, how do we run this in the original tree and do it at every iteration? Let's think about it. What observation do we have here? We have that we are gonna run it here, and we can directly check if if the root and the subroot are the same, we have to return true, right? And we can stop. And if not, we are gonna continue. So now if it's true, we can do a early stop. So I'm gonna say if I think it's in this way, if self dot is same tree of root and sub root, we're gonna return true. Otherwise, it means that it is continuing, right? And if it reaches the end, so it means that it tries to find when the root is empty, I gotta return false. So if not root, I'm gonna return false. And if we are at this node and we check this sub-tree, if this is not the case, like this node is not equal to this one, then I'm gonna run it for these children and check if this node is equal to this one, like if this tree from here is equal to this tree. So I just need to run it for both children, so I'm gonna say return, we're gonna run the function delf is sub-tree for the left root and the right root. And in this case it's just an OR statement, because if it's true for either the left or the right side, then we find something. It doesn't need to be true for both of them. There's a mistake. What is the mistake? Takes two positional arguments, but 3 were given. What? I mean, I'm just giving root and subroot. Okay, I mean, it could be related to this. So let's move this and remove the self. And remove this one. Maybe there is an overloading or something. I don't want to risk it. Okay, I see. Yeah, maybe it's the name. Let's change the name. And what it's saying, cannot access local variable same where it's not associated with a value. Ah, yeah, makes sense. So we didn't check if it's no, wait, what? Okay, maybe the order of the function. Okay, yeah, now it should work, because we are. And where is the mistake now? Subroot. Okay, yeah, for sure. I'm missing subroot. So I'm calling sub-tree on root left and subroot, and on root right and subroot. What is error now? Okay, I misspelled right. Okay, it's fine now. Okay, good. So that's it for today, and yeah, that's it.